Welcome to the video lecture on Taylor polynomials and approximations. Our objective in this section is to find a polynomial approximation for a non-polynomial function. We'll start with an example. Suppose that we want to find a polynomial function p sub n of x, which best approximates the trigonometric function cosine of x near 0. So what kind of features should this polynomial have if it's going to be a good approximation to cosine of x near 0? Well, one obvious thing that we would probably want to happen is we would want the polynomial to go through the same point at 0 that cosine goes through at 0. So we could write that as p sub n of 0 needs to equal f of 0 so that they both go through the same point. Okay, another condition that we might require is that the derivatives should be equal. So the derivative at 0 should equal to the derivative of cosine at 0. Now, why would we want that? Well, remember, slope kind of gives the direction of a curve. So if the slopes are the same at 0, then that helps the polynomial go in the same direction that the original function cosine would go in as well. So this way we're having so that both slopes are equal. And that way the polynomial sort of fits the same direction as the original curve as well. Now if we wanted additional derivatives to be equal, like the second derivative, then that would force the concavity to be the same at 0 and so forth. So we could add additional requirements by looking at other higher order derivatives as well. So we could add further requirements by looking at additional derivatives. So what we're going to do first is we're just going to see if we can come up with a linear approximation to the cosine curve. So just what line looks like and best fits the cosine curve near 0. So that's what we're going to come up with. So our original function is cosine of x, and our linear function that we're going to try to figure out what it is would have the form mx plus b. So if we want the 2 points to be equal at 0, then let's go ahead and see what those values would be. So at 0, cosine of 0 is equal to 1. And at 0, this x would go to 0 and we would just get this constant b. So if we want f of 0 to equal p1 of 0, then that forces the b value of our line to be 1. Now if we want the derivatives to be equal, then let's go ahead and compute our derivatives. The derivative of cosine is minus sine of x. So at 0, sine of 0 is 0. If our line is mx plus b, then the derivative of that would just be m. And at 0, since there's no x left, this is going to stay m. So if we set our two derivatives equal to each other, then that forces our slope m to be 0. So what would this equation be? Well, if m is 0, there's no x term, and if b is 1, then this p sub 1 of x is actually just the horizontal line y equals to 1. So that would be our linear approximation. Now, do you suppose that that's a good approximation to the cosine curve? Definitely not. It's a horizontal line, and we know that the cosine curve goes up and down and up and down. So how could we make this approximation better? Well, we could increase the degree on our polynomial approximation. So let's consider a quadratic function instead that would approximate cosine of x. So if that is to happen, then we would want our function cosine to equal to our polynomial at 0. We would want our first derivatives to be equal, and we would want our second derivatives to be equal as well. So we know that cosine of 0 is 1, and if we plug in 0 for x over here, then these two x terms go away, and we would just get c. So that forces the value of c to be 1. The first derivative would be minus sine of x, and at 0 that is equal to 0. And if we take one derivative of this quadratic, we would get 2ax plus b. And if I plug 0 into that, then this x term goes away and we would just get the constant b. So that tells us that our b coefficient must be 0 if the first derivatives are to be equal. Now let's look at the second derivatives. The second derivative would be the derivative of negative sine x, which is going to be negative cosine x, and at 0 that's equal to negative 1. If we look at the second derivative of our polynomial here, that would be the derivative of this first derivative, which just goes to 2a, which is a constant. So when I plug in 0, it's going to stay 2a. So that forces 2a to have to equal negative 1, which implies that a has to equal negative 1/2. So what would be the equation of this quadratic? Well, we just found out that the a coefficient has to be negative 1/2 x squared, so that our second derivatives are equal. The b goes to 0, so there's no x term at all, and the constant term c is just 1. So this would be our second degree polynomial approximation to the cosine curve. And as you might suspect here, the higher the degree of your polynomial, the better the approximation is going to be. So let's boost it up a little bit more, and let's look at the fourth degree polynomial approximation for cosine. So let's just go ahead and do everything for cosine here first. We know that cosine at 0 is 1. The derivative of cosine is minus sine. The second derivative would be minus cosine. The third derivative would become positive sine of x, and the fourth derivative goes back to cosine of x. So if I plug in 0 into these derivatives, the first derivative at 0 goes to 0, since sine of 0 is 0. Cosine of 0 is 1, so this will be negative 1. Sine of 0 is back to 0 again, and cosine of 0 is back to 1. So those are all my derivatives for cosine. Now let's look at our derivatives for our fourth degree polynomial. Initially, when I plug in 0, all of these terms go to 0 except the constant term e. So this will be e. One derivative is going to give me 4ax cubed plus 3bx squared plus 2cx plus d. A second derivative will give me 12ax squared plus 6bx plus 2c. A third derivative will give me 24ax plus 6b, and a fourth derivative will just give me 24a. So if I plug in 0 into these four derivatives, all of the x terms go to 0, so this is just going to leave me with the constant term d. This will leave me with the constant term 2c. This will leave me with the constant term 6b, and this is already a constant, so this will stay 24a. So if I want the fourth derivatives to be equal, and I set them equal to each other, then that tells me that a has to be 1/24. If I want the third derivatives to be equal, then 0 has to equal to 6b, so that tells me that b is just 0. If I want the second derivatives to be equal, then negative 1 has to equal 2c, so c is negative 1/2. If I want the first derivatives to be equal, that forces d to be 0, and if I want the functions to be equal at 0, then that forces e to be 1. So this is going to be a 1, this will go to 0, c will be negative 1/2 x squared, b will go to 0, and a is 1/24. So my polynomial is going to look like 1/24 x to the 4th minus a 1/2 x squared plus 1. All the odd terms, sorry about that, all the odd terms here disappeared because those derivatives went to 0. So here is what we call our fourth degree polynomial approximation to cosine. Now, I've already pre-written down the decimals, but I'll show you how I got them. What we're going to look at next is how well these polynomials approximate the function when we are close to 0 or farther away from 0. So cosine of x, all I did was I evaluated it at 0.1, 0.5, 0.75, 0.9, and cosine of 1, and that's what all these decimals are here. Then I took our second degree polynomial, which remember was just negative 1/2 x squared plus 1, and I plugged in those same input values, and these are the values that we got here. And then for this fourth degree polynomial, I plugged in all of these inputs, and these are the values that I got here. Now for a quick, easy way to do that on your calculator, you can do this using lists. So if you go to Stat and then Edit, you can create your lists. In List 1, I just typed in those X values that I wanted to look at. In List 2, I arrowed over up to the top of L2, made sure that it was highlighted and pressed Enter. And then I just typed in cosine of L1 because it's L1 where we're getting our inputs from. And so these were all those first values in the table. And then in L3 I typed in the negative 1/2 x squared plus 1 formula, but instead of using x I used L1. And if you arrow over once to the right, in L4 I typed in the formula for that fourth degree polynomial, 1/24 L1 to the fourth minus 1/2 L1 squared plus 1. So that's a quick, easy way to get all of those values at once without having to type in a bunch of numbers. So that's how I got them. Now let's look at the data here and see what it tells us. Now remember, we were looking at this approximations, trying to find approximations near 0, x equals to 0. So these values up here represent values of x close to 0, and then this value down here is a little bit farther away from 0. So right close to 0 at point 1, all three of these were equal. At point 5, when we got a little further away from the 0 value, these start getting a little further off, but you'll see that the P4 value here is a little closer to the true value than the P2 value. When we move a little bit further away from 0 this way, now the values for P2 and P4 again are a little bit off, but P4 seems more accurate to the true value than P2. As we get further away at point 9, again, these are starting to veer off course a little bit more, but P4 seems more accurate. And then at 1, we can see that for P4 we're still at least 0.54, but at P2 we're only at 0.5. So the conclusions that we can make here is that the higher the degree of the polynomial, the better the approximation. And also, the further that you got away from 0, the worse the approximation got. We were much better at values close to 0 than we were at values farther away from 0. Now, in general, to find a polynomial approximation p sub n of x for a function f for values of x near 0, we will construct this polynomial so that every derivative matches for the polynomial and for the function for every k. So if this is a generic nth degree polynomial with constant terms c sub 0 plus c1 plus c2 x squared plus c3 x cubed and so forth, all the way up to c sub n x to the n, what we're going to want to try and do is come up with a formula for what these coefficients would have to be so that this condition that the derivatives are equal to each other is maintained. So initially our polynomial is this c sub 0 plus c1x plus c2x squared plus c3x cubed plus c4x to the fourth and so on, all the way up to c sub n x to the n. So if I take one derivative of that, this constant term c sub 0 goes away, and we're left with c1 plus 2c2x plus 3c3x squared plus 4c4x cubed plus 5c5x to the fourth, and then this last term will be n c sub n x to the n minus 1. If I take two derivatives, this constant goes away, and I'll have 2c2 plus 3 times 2 times c3x plus 4 times 3 times c4 times x squared plus 5 times 4 times c5 times x cubed, and so on, down to n times n minus 1 c sub n x to the n minus 2. And you could multiply this and make this 6, 12, 20, and so forth. But I'm going to show you the pattern here that develops by leaving it written out as this product. If I do my third derivative, this constant goes away, and I'm just left with this 3 times 2 times c3 plus 4 times 3 times 2 c4x plus 5 times 4 times 3 c5x squared, and so on, down to n minus 1, n minus 2, c sub n x to the n minus 3. If I do 4 derivatives, this term is gone, and I get 4, 3, 2 times c4 plus 5, 4, 3, 2, c5 times x, and so on. And this is n times n minus 1 times n minus 2 times n minus 3, c sub n x to the n minus 4. And let's do one more here. If I do a fifth derivative, this term goes away, and we're left with 5, 4, 3, 2, c5, and so on. And then this would be n minus 1, n minus 2, n minus 3, n minus 4, c sub n times x to the n minus 5. Now eventually, when I take my nth derivative, all of these lower order terms are going to disappear, and the only term that will be left would be from this highest power term. When you take n derivatives, then this power x to the n finally gets down to a 1. But what are going to be all the coefficients in front of it? If we look at this pattern here, what it looks like it's going to be is n minus 1, n minus 2, n minus 3, n minus 4, n minus 5, and so on, all the way down until that power goes down to 1. And then we'll also have that c sub n in there as well. Now, what is this product right here also known as? When you take a number and you multiply it by the next lowest integer each time, like 5 times 4 times 3 times 2 times 1, that's called a factorial. So this is just n factorial times c sub n. So if I plug 0 into that, since this is already a constant, I'm just going to get n factorial c sub n left over. There's no x's left to plug in for. So how do we solve this equation right here for c sub n? We're trying to come up with a formula for what these c sub n's are going to be. Well, all I'd have to do to solve for c sub n is divide both sides here by n factorial. So that would be this nth derivative of the polynomial at 0 divided by n factorial. And remember, we wanted our all of our derivatives to equal to the function's derivatives as well. So this nth derivative of p sub n would also equal to the nth derivative of the function at 0, because we want those derivatives to match. So this gives us a formula for all of these coefficients. They're just the corresponding nth derivative of the original function with 0 plugged in divided by that n factorial. So what this would look like is, for the very first term, that's just going to be the function evaluated at 0, no derivative at all. For the first term, or for the first derivative, this would be f prime of 0 over 1 factorial times just an x. For c sub 2, this would be the second derivative at 0 or divided by 2 factorial times x squared. For the third derivative, c3, this is going to be f triple prime of 0 times x cubed over 3 factorial, plus the fourth derivative at 0 times x to the fourth over 4 factorial, and so on, up to the nth derivative at 0 over n factorial times x to the n. So the degree of the term matches the degree of the derivative that you're taking, and it also matches the degree of the factorial that you're dividing by. So x cubed over 3 factorial, x squared over 2 factorial, etc. This polynomial right here is called the Maclaurin polynomial of f of x at 0. And it works really well to approximate values of any function near 0. So we're going to talk a lot today about how you come up with these Maclaurin polynomials. Now you can also look at polynomials that aren't looking right at 0. What if you wanted to look and approximate a function at a value a? Well, what we can show is that there's a polynomial for that as well that looks at the kth derivative evaluated at a divided by k factorial times x minus a to the kth. So it looks just like this Maclaurin polynomial up here, except you're plugging in that a value for all of these derivatives, and instead of having terms that are just x, x squared, x cubed, x to the fourth, and so on, they're actually going to be x minus a's, x minus a squared, x minus a cubed, x minus a to the fourth, and so on. But all the rest of this looks the same. So when you're looking at a point other than 0, and you're looking at a point at a instead, this is called a Taylor polynomial. So a Maclaurin polynomial is a Taylor polynomial, it's just using a to be 0. It's kind of a special case. And we'll talk about Taylor polynomials as well in a little bit. Let's practice finding the fourth degree Maclaurin polynomial for the cosine function. So remember what this fourth degree Maclaurin polynomial has to look like. It's going to be this function cosine at 0 plus f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial times x squared plus the third derivative at 0 divided by 3 factorial x cubed, and then the fourth derivative at 0 divided by 4 factorial times x to the fourth. Okay, so there's a nice pattern there. So what we want to do is figure out what each of these derivatives is, plug in 0, and then we'll know what all of these numerators are going to be, and we'll be able to easily write out our polynomial. So our original function is cosine. So let's find these four derivatives first. The first derivative will be minus sine of x. The second derivative, the minus stays there, and this just goes to minus cosine. Triple derivative becomes positive sine of x, and the fourth derivative goes back to cosine of x. Now all we have to do is plug in 0 into each of these. So cosine of 0 is 1, sine of 0 is 0, negative cosine of 0 is negative 1, sine of 0 is 0, cosine of 0 is 1. So that means this goes to 1, this goes to 0, so that whole term will go away. The second derivative goes to negative 1. The third derivative goes to 0, so the whole term disappears, and the fourth derivative goes to 1. So this is going to be 1, this term is gone, minus negative 1 over 2 factorial times x squared, plus this goes to 0, and this is going to be 1 over 4 factorial x to the fourth. And if you think about what these values are, 2 factorial is just 2 times 1, so that's just 2. And 4 factorial is 4 times 3 times 2 times 1, which is 24. And this is exactly that same P4 that we got earlier when we were trying to come up with our fourth degree polynomial approximation to cosine at 0. So the Maclaurin polynomial is exactly what we ended up with. Let's find the nth degree Maclaurin polynomial for the function e to the x. So that's going to look like f of 0 plus f prime of 0 over 1 times x plus f double prime of 0 over 2 factorial x squared, and so on, up to the nth derivative at 0 over n factorial times x to the n. So to get all of these coefficients in the numerators, we need some derivatives. The nice thing is that our function e to the x is its own derivative. So the first derivative would be e to the x, the second derivative e to the x, the third derivative e to the x, the kth derivative would be e to the x in general. So therefore, at 0, e to the 0 is 1, so all of these derivatives are going to be 1 as well. So this will be 1, 1, 1, 1, and 1. So this is going to be 1 plus 1 over 1 times x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, all the way up to 1 over n factorial x to the n. So 1 plus 1 over 1 factorial x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, all the way up to 1 over n factorial x to the n. And sometimes we just write this as 1 plus x over, or just x, sorry, x over 1 is just x, plus x squared over 2 factorial plus x cubed over 3 factorial, all the way up to x to the n over n factorial. And you can expand these out if you want. Make this 2, make this 6, and so forth. But there is our polynomial approximation. So what we're really saying here is that e to the x is approximately going to act and look like this nth degree polynomial. And the bigger that degree gets, the better this approximation will be. That's the purpose of these Maclaurin and Taylor polynomials. So let's try a Taylor polynomial now. So the big difference between Taylor polynomials and Maclaurin polynomials is that Taylor polynomials are centered around a different point other than 0. So we want the fourth degree Taylor polynomial for the ln function at 1. So we want to center this at 1. So this is what it would look like. It's going to have all those derivatives again, but it's going to evaluate those derivatives at 1. And instead of just having x squared, x cubed, and x to the fourth, it's going to be x minus 1, x minus 1 squared, x minus 1 cubed, and x minus 1 to the fourth. So you're sort of shifting or centering that x around your 1. So just as before, to find out this polynomial, we need to know all these derivatives so we can know what these coefficients are. And then we're just going to substitute them in, and we'll have our derivative. So ln of x has as its derivative 1 over x, which we can think of as an x to the negative 1. So the second derivative would be negative 1 x to the negative 2, or negative 1 over x squared. The third derivative becomes positive 2 x to the negative 3, or 2 over x cubed. And the fourth derivative is negative 6 x to the negative 4, or negative 6 over x to the fourth. Now we can't evaluate this at 0 because ln isn't defined at 0. So that's why we have to use a Taylor polynomial at some other value than 0, like at 1. So now all we're going to do is we're going to plug in 1 into all of these values. So ln of 1 is 0. 1 over 1 stays 1. Negative 1 over 1 squared is negative 1. 2 over 1 is 2. And negative 6 over 1 is negative 6. So this becomes a 0. This becomes a 1. This becomes a negative 1. This becomes a 2. And this becomes a negative 6. So if we plug those in, this is going to be, this goes away, so we'll just have a 1 out front times x minus 1. Then we'll have a minus 1 over 2 factorial times x minus 1 squared, plus a 2 over 3 factorial x minus 1 cubed, minus a 6 over 4 factorial x minus 1 to the fourth. And you can leave it like that if you like. If you want, you can reduce it a little bit. I'm just going to reduce the coefficients. Do not bother foiling out, cubing out, raising to the fourth, any of these x minus 1s. Just leave them as a quantity raised to a power. So this coefficient here just becomes a minus 1/2. 3 factorial is a 6, so 2 over 6 is just going to be a 1/3. And 4 factorial is a 24, so 6 over 24 is just going to be a minus 1/4. So we just get out front 1 over that degree. Okay, so here is our polynomial approximation to the ln function. So this is approximately what ln of x would look like near 1. Okay, this is just near 1. It would be a different function altogether if we were looking at the ln at some other a value. Okay, so I already typed into my calculator some values here so that you could see. So let's look at the ln of 1.1. So that's pretty close to 1. The true value of ln of 1.1 is 0.09531. If I plug in 1.1 in for these x's and punch that into my calculator, I get 0.09531 as well. So very good, very close, very equal approximation here. Very good estimate. If I look a little bit further away from 1 and look at 1.5 instead, then this true value is supposed to be 0.405465. But when I plug in 1.5 for all of these x's here, then that's actually going to give me 0.40104. So I'm getting a little bit less accuracy because we're getting a little further away from 1. Okay, so just keep in mind, the higher the degree of your approximation, the better it's going to be. But the further away that you get from that center point, the less accurate you're going to be as well. Okay, let's go back and find another Maclaurin polynomial. This time we're going to find it for the function sine of pi x. So remember, a Maclaurin polynomial is centered at 0, so you're plugging in 0 into all of your derivatives, and you're just going to have an x squared, and an x cubed if we want the third degree polynomial. So let's start by finding our derivatives. Our function is sine of pi x, so one derivative of that is going to be a cosine pi x times pi, and I'll put that pi out front. If I take two derivatives, the derivative of cosine is a minus sine of pi x, but we're multiplying by another pi times the pi that we already had out front, so that makes us a pi squared. And if I take a third derivative, the derivative of sine is going to go back to cosine of pi x times another pi. So pi squared times another pi would be pi cubed, and this minus sticks around. So now if I plug in 0, sine of 0 is 0. Cosine of 0 is 1 times that pi, so this will be pi. Sine of 0 is 0, so this whole thing goes to 0. And cosine of 0 is 1, so I just get this coefficient negative pi cubed out front. So this will be 0, this will be pi, this will be 0, so this whole term goes away, and this will be negative pi cubed. So this is gone, and we just get pi times x. This term is gone, and we get minus pi cubed over 3 factorial times x cubed. And if you want, you could write that as pi x minus pi cubed over 6 times x cubed. So there is our third degree Maclaurin polynomial for the function sine of pi x. Alright, now let's try a fourth degree polynomial, Taylor polynomial, for the square root function centered at 4. So this time we're going to be doing a fourth degree polynomial, and we're going to be centering at 4, so all of these derivatives need to be evaluated at 4, and each of my x's is actually going to be the quantity x minus 4 raised to some power. So let's start with finding our derivatives. Square root of x is x to the 1/2, so when I take the derivative of that, I'm going to get 1/2 x to the negative 1/2. This is the same as 1 over 2 square root of x. If I take another derivative, a 1/2 times a negative 1/2 is a negative 1/4, x to the negative 3/2. So this is negative 1 over 4 times the square root of x cubed. If I take another derivative, negative 1/4 times negative 3/2 is positive 3/8, x to the negative 5/2. So this is 3 over 8 times the square root of x to the 5th. And then finally here I'm going to get negative 15/16 x to the negative 7/2. So this is negative 15 over 16 square root of x to the 7th. Now we're plugging in 4. That's our center point for this Taylor polynomial. So we need the square root of 4 to start off, which is just 2. And then we want 1 over 2 times the square root of 4. So that's going to be 1 over 2 times 2, so this is a 4th. And then if I plug in 4 into this, I'm going to get 1 over 4 times the square root of 4, and I'm actually going to do that cube after I do my square root to make the number get smaller. So square root of 4 becomes a 2, and then when I cube it, it becomes an 8. 8 times 4 is 32. Then this would be 3 over 8 times the square root of 4, and then I'm going to raise that to the 5th. So square root of 4 is 2, 2 to the 5th is 32, 32 times 8 is 256. And then the last one here, negative 15 over 16 times the square root of 4 raised to the 7th, and this is going to give me negative 15 over 2048. So now I know all of these different coefficients. So f of 4 is just 2, that's our constant term. Then we have plus our 1/4, that's this f prime, over 1 factorial, which is just a 1, times x minus 4. Then we're going to get our negative 1/32 over 2 factorial times x minus 4 squared. Then we're going to get our 3 over 256 divided by 3 factorial times x minus 4 cubed, and then minus 15 over 2048 over 4 factorial times x minus 4 to the fourth. And if we clean that up just a little bit, this is 2 plus 1/4 x minus 4. When you take 1/32 and you divide it by 2, that just becomes 1/64. You're basically just multiplying these two denominators by each other when you flip over 2 factorial. So when I flip over 3 factorial, it becomes a 1/6 times 3 over 256. And the 3 would cancel, and doing a little reducing on the fractions, this is 1 over 512. And then if I multiply 15 over 2048 times the reciprocal of 4 factorial and I do some reducing, that gives me minus 5 over 16,384 times x minus 4 to the fourth. So there is our 4th degree polynomial approximation. Now, an approximation is of little or no value unless we have some kind of idea as to its accuracy. So to measure the accuracy of a Taylor or Maclaurin polynomial, we're going to consider the concept of its remainder. And we've talked about remainder in the past when we were doing some of our series tests. So the exact value of the function would be f of x. The polynomial approximation would be this p sub n of x, and then the remainder we're going to call r sub n of x. So what you can see is that the exact value would be the approximation plus the remainder. So if I solve this sort of equation here for the remainder, that means the remainder is the exact value minus the approximation, and in absolute value, this remainder would be the absolute value of the exact value minus the approximate value. So what that leads us to is something called Taylor's theorem with the Lagrange form of the remainder. So this is going to be a way of estimating what that remainder will be if you make a approximation using an nth degree polynomial. So what we're doing is we're taking a function f, we're centering this at some value c, and we're using the Taylor polynomial at c. So that would be f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times x minus c squared, all the way up to this nth derivative over n factorial times x minus c to the n. So this part here is just our Taylor polynomial approximation. And it's an nth degree polynomial. And then on the end of this, what we're adding on is that remainder. So here's the approximation, and then if we add the remainder onto it, we should get the exact value. So what are we going to use for this remainder? Well, this is what the Lagrange formula tells us. The remainder r sub n, by using an nth degree Taylor polynomial, you can bound this remainder by the nth plus 1 derivative evaluated at some number z divided by n plus 1 factorial times x minus c to the n plus 1. The z value that we're going to use here is something between the x that we're trying to approximate and the c value that we're centering our polynomial at. So we're going to do a few of these so you get the hang of it. But basically this is saying that this remainder can be approximated by the nth plus 1 derivative evaluated at z over n plus 1 factorial times x minus c to the n plus 1. In other words, the very next highest term in that Taylor polynomial if you were to keep going. So this is kind of our formula right here. Now usually we're not able to find the z that's going to maximize this derivative. What we usually do is we find some bounds for this nth plus 1 derivative, and we use it to kind of bound the size of our remainder. And the actual remainder is typically much, much smaller than the bounds that we come up with. Okay? So here's an example. Use Taylor's theorem to approximate e to the first by using a 5th degree Maclaurin polynomial and determine the accuracy of the approximation. So our original function that we're trying to approximate is e to the x. We know that every derivative of e to the x is e to the x back again. Therefore, every derivative at 0 is going to equal 1, since e to the 0 is 1. And we're trying to use a Maclaurin polynomial here, so that means we're centering this at 0. So what would this Maclaurin polynomial look like, this fifth degree polynomial? Well, remember, it's going to be the original function value at 0 plus f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial times x squared, and so on up to, since we want a fifth degree, the fifth derivative at 0 over 5 factorial times x to the fifth. Since the derivative and the function at 0 is always 1, all of these coefficients are just going to be 1s. So that means this fifth degree polynomial is going to look like 1 plus 1 over 1 is just 1 times x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the fourth plus 1 over 5 factorial x to the fifth. So that's our Taylor approximation to the function e to the x. Now we're going to use this to approximate the value of e to the 1. So instead of plugging in 1 into e to the x, maybe we don't know what that function is, we're going to use this polynomial instead. And in fact, this is what your calculator does. When you type in e raised to the first power and you hit enter on your calculator, it's actually using a very accurate Taylor or Maclaurin polynomial approximation to the e to the x function to get you the decimal equivalent of what you're asking it to do. So it uses these polynomial approximations to get the values that your calculator tells you. So if I plug in 1 in for all of these x's, this is going to be 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial. And if you compute that as a decimal, it's approximately 2.716 repeating. Okay, so we know that that's not quite accurate because e to the first is really 2.71828. So we're a little bit off here. So what would our remainder be? Well, according to this Lagrange formula that we just talked about, the remainder term is going to be the next highest term that we stopped at. So if we stopped at the fifth derivative and the x to the fifth over 5 factorial, then the next highest term would be the sixth derivative times x to the sixth over 6 factorial. Now notice I'm not putting a 0 in here because actually what this Lagrange formula says is we have to use a z, where the z that we use is between the center point that we're looking at, which was 0 since we were using a Maclaurin polynomial, and the actual x value that we're plugging in to estimate. And we're trying to estimate this at 1. So the z value that we pick needs to be something between 0 and 1. So since we know that the sixth derivative of e to the x would just be e to the x back again, then the sixth derivative at z would be e to the z back again. So what we want to try to do is we want to try to bound this e to the z. When we're doing these Lagrange problems, we're really trying to find a bound for that derivative any way that you can. So if we know that z is between 0 and 1, then that means e to the z would be between e to the 0 and e to the 1. And e to the 0 is 1, and e to the first is that, 2.7 whatever, but we know that that's definitely less than 3. And for the sake of using nicer numbers instead of yucky decimals, I'm going to bound e to the z by the number 3. So I'm going to say that this value right here is less than or equal to 3 times x to the 6th over 6 factorial. So this remainder has to be smaller than or equal to this bound. Okay, now what do we know our x to be? What was the x that we plugged in up here when we were approximating e to the 1? We were plugging in 1 for all of these x's. So I'm going to plug in 1 for my remainder x as well. So this becomes 3 times 1 to the 6th over 6 factorial, which is just 3 over 6 factorial, which is reduced 1 over 240, or as a decimal, 0.00416, repeating. So what we've just found out is that the remainder that we incur by only going up through a 5th degree polynomial is at most 0.00416. So what does this tell us about e to the first? Well, it means that e to the first is going to equal this 5th degree approximation that we came up with right here, so 2.716 repeating, plus this remainder that we just came up with right here. So it gives us kind of a bound on the true value of e. So the true value is going to be bigger than our approximation, but less than our approximation plus this remainder. And as a decimal, that's 2.72083 repeating. So the true value of e lies somewhere between 2.716 repeating and 2.72083 repeating. And we know that it does, okay? So this gives us a way of determining sort of our accuracy level of our approximation. Let's try another example. This time we're going to use a 3rd degree Maclaurin polynomial. So we're centering it at 0 because we're using a Maclaurin. And we want to use a 3rd degree Maclaurin polynomial to approximate the inverse tangent of 0.5. And this again is exactly what your calculator is probably doing. It's using a polynomial approximation for this inverse tangent function, plugging in 0.5 into that polynomial, which is a much quicker, easier calculation for it to make, and then getting its estimate from that. Okay, so we want to do this with a 3rd degree Maclaurin polynomial and determine the accuracy of our approximation. So recall that when we are talking about a 3rd degree Maclaurin polynomial, we're looking for, f of 0 plus f prime of 0 over 1 factorial times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial x cubed. And we need to find all of these coefficients. So the original function is the inverse tangent of x. So the inverse tangent of 0, what angle when you take the tangent of it gives you back 0? Well, that's just 0. Now if I compute the derivatives, I already did that for you. The first derivative of the inverse tangent is 1 over 1 plus x squared, and then you can just use a quotient rule and do some simplifying to get the 2nd and 3rd derivatives here and here. So now let's plug in 0 into these derivatives. So this is going to be 1 over 1 plus 0, which is just 1. This one, when I plug in 0 in the numerator, it makes that whole numerator go to 0, so the whole fraction goes to 0. And then the 3rd derivative, this term goes to 0, so in the top we get 2 times negative 1, which will be negative 2, over 0 plus 1, which is just 1. So this is going to be negative 2. So this term is 0, and the 2nd derivative is 0. The first derivative was 1 times that x, plus the 3rd derivative was negative 2 over 3 factorial x cubed. So simplifying that, that's going to be x minus, if I cancel out the 2 here, this is just going to be a 1/3 x cubed. So there's our Taylor polynomial, or a Maclaurin polynomial, degree 3. What would be the value of this at 0.5, the value that we're trying to approximate? Well, if I plug in 0.5 into this and use my calculator, I'm going to get 0.4583 repeating. So now what we want to do is come up with how much remainder is there as a result of only using a degree 3 polynomial. How much error have we incurred? So what the Lagrange formula tells us is that the remainder term, by using a 3rd degree polynomial, is actually going to be the 4th derivative at some number z divided by 4 factorial times x to the fourth. And once we find a bound for this derivative, which we're going to do in a moment, then what we're going to do to find the remainder that we incur at this actual value is we're going to plug in 0.5 in for that x. So we're going to have to figure out a bound for this fourth derivative. We'll do that in a moment. And then we just divide that by 4 factorial, and then we take 0.5 to the fourth, and whatever that is going to be my remainder. So how do we bound this fourth derivative? Well, first we need to find it, okay? So if this is my third derivative, then my fourth derivative is going to require doing a little bit of a quotient rule here. So we're going to do the bottom times the derivative of the top. If you distribute across the top here, this numerator is really just 6x squared minus 2. So the derivative of that is just going to be a 12x minus the top times the derivative of the bottom, which will be a 3 brought down, and then x squared plus 1 quantity squared times 2x. Use your chain rule on that. And then in the denominator, we're just going to have the bottom squared, and it was already raised to the third, so when I do a cube raised to a square, that becomes a 6th power. So let's clean this up here a little bit. What I can do on the top is I can factor out some x squared plus 1s. I've got 3 of them here, but only 2 of them here, so I'm going to pull out 2. And then a 3 times a 2x times a 2 is actually a 12x. So I'm also going to pull out a 12x. So this is all gone, but I have one of these x squared plus 1s left. This is gone, this is gone, this is gone, and this is gone. So all I have left is this minus and this 3x squared minus 1. So when I distribute that minus across, it becomes negative 3x squared plus 1. So reducing here, I'm going to go ahead and cancel out 2 of these with 2 of them on the bottom. So the bottom becomes raised to the fourth. And when I simplify inside there, I'm going to get a negative 2x squared plus 2. And if you just want to kind of rewrite that a little bit, I can factor out a 2 and make this a 24x. And then this would be 1 minus x squared inside the parentheses. So there's my fourth derivative. Now what we want to do is we want to bound it. So I'm going to show you 2 options here. The easier way to bound this is going to seem a little bit strange, but first what we want to keep in mind is what we know about this z. We want to really evaluate this at some z. So the fourth derivative at z would be 12z times 1 minus z squared over z squared plus 1 to the fourth. And what we know about z is that it's between the point that we're centering our polynomial at. And this was a Maclaurin polynomial, so we're centering it at 0. So the z has to be bigger than 0. And then it has to be less than the value that you're plugging in for your x, which is this number that we're plugging into our inverse tangent. So it has to be smaller than 0.5. So the easy way to do this without a whole lot of work is to look at your fourth derivative and figure out what values of z could you use to make this become as large as possible. When you bound it, you're trying to find the largest possible error that could possibly happen. So we want to make this as large as possible. And it's not necessarily going to be the same z throughout. What I like to do is I look term by term here and I figure out which z in this interval is going to make that particular term as big as possible. So for example, if this z needs to be as big as possible, what value of z on this interval should I choose that's going to be the biggest z? Well, that would be the right endpoint, 0.5. So if I use 0.5 for this z, that makes this term get as big as possible. Now look at this term individually. What z could you use here to make this whole expression get as big as possible? Well, this time, since we're subtracting z squared, we actually want z to be as small as possible so that the difference gets as big as possible. So in this case, I'd actually want to use a z of 0. And in the bottom, since this is the denominator, we want to make the whole fraction as big as possible, and the only way to make a fraction get big is to make its denominator get small. So again, we want to pick the smallest z that we can so that this denominator gets as small as it can. And the smaller of the two z's here would be the 0. So on these bounding problems, you're not necessarily always using the same number for z throughout the entire derivative. You might use one endpoint for one part and one endpoint for another part. So what does this come out to? Well, 1 minus 0 squared is 1. 1 to the 4th is 1. So this is really just 12 times this 0.5. Oops, I think I lost my 2, didn't I? I forgot my 24. This was supposed to be 24x, and I wrote 12. Sorry about that. So this was a typo on my part. I forgot that I had factored it out and I was looking in the wrong place. So we should have been using this 24 here and here. So now 24 times a 0.5, or 24 times a half, is just 12. These go to 1, so the whole derivative can be bounded by 12. That's as large as it could possibly get, which means that this value up here is definitely smaller than or equal to 12 times 0.5 to the 4th over 4 factorial, which reduces to 0.03125 as a decimal. It's 1/32. Okay, so that's one way to bound your derivative. That requires very little work. You're just kind of spot checking what value of z on the interval that you're supposed to be looking at for z, which value or which endpoint should you be plugging in to make each piece get as big as possible, because we want the largest possible error bound just to be safe. If we make it too small, then we might be undercutting what the true error is. Now there is another option here, and that would be to take this fourth derivative and actually graph it. So we could graph this fourth derivative on our calculator. And if you do a proper amount of zooming, it's going to look something like this. And you'll see that it has a maximum right here. And you can use that max command on your calculator. It's under Calc, underneath your graphing window. So you can find the maximum by doing a left bound, a right bound, and a guess. And you can find that the coordinates of this maximum are 0.325, 4.6685. So that means the largest height that this takes on is this y value here. So the largest value of this fourth derivative is that maximum when we're looking between 0 and 0.5 for our z's. So the largest that this takes on for any z is going to be that maximum value. And you can see that the bound that we got over here, which was 12, is actually much bigger than that 4. And that's okay. Usually that's the case. Usually the bound that we come up with is much bigger than the true bound that would exist for that particular derivative. And that's okay. Just use whatever is easiest. This to me takes more work, even though it might give you a more narrowed range of values for that remainder. Okay, so what we're going to conclude here then is that our remainder was equal to, or less than or equal to, that 12 times 0.5 to the 4th over 4 factorial. The 12's coming from that bound on our fourth derivative. You could also have plugged in that 4.6 number in here instead if you want a smaller bound. But I'm just going to stick with my 12, and that means that this remainder is less than or equal to 0.03125. If we had used this 4.6 number right here instead, then obviously this remainder would be smaller. Okay? So it's up to you. As long as you're showing your work and justifying where that bound is coming from, you could do it either way. But the actual error tends to be much less than the bounds that we come up with by hand. All right, let's determine the degree of the Maclaurin polynomial so that the error in approximating e to the 0.75 is less than 0.0001. So this time I'm telling you slightly different information. I'm not telling you to use a third degree Maclaurin polynomial or a fourth degree. I want to know what degree I need so that the error that's incurred is smaller than 0.0001. Okay, so what do we know about the Maclaurin polynomial for e to the x? Since the derivative of e to the x is always e to the x back again, and e to the 0 is always going to be 1, then we know our Maclaurin, polynomial for e to the x in general just looks like 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. The derivatives in general are going to be that e to the x back again. So if I approximate e to the 0.75 by using an nth degree polynomial, and we don't know what this n should be yet, but if I use an nth degree polynomial, then the Lagrange theorem says that the remainder by using an nth degree polynomial would be the nth plus 1 derivative at z over n plus 1 factorial to the x, or times x to the n plus 1. So my nth degree polynomial would look like this, and so this term right here would be the very next term in this polynomial. Now the derivative of e to the x is always e to the x back again, so the derivative at z would be e to the z back again. So we're going to bound this by looking at a bound for e to the z. And since z has to be between 0, which is our centering point since we're using a Maclaurin polynomial, and 0.75, since that's the value that we're trying to plug in for x, then that means e to the 0 should be between the e to the z should be between e to the 0 and e to the 0.75. Now again, to make the numbers nicer so that we're not dealing with decimals, let's take e to the 0.75 and realize that it's less than e to the 1, and e to the 1, which is about 2.7, is obviously less than 3. So we're picking an actual bound for this derivative that's probably a lot bigger than what it should be, but we're picking something that's easy to use. So we're going to bound this derivative by 3. Since we know it's got to be e to the something where that power is less than 1. So the remainder has to be 3 over n plus 1 factorial x to the n plus 1. So the remainder of using 0.75 would be this formula with 0.75 plugged in for x. So that's what this is right here. And what we want to determine is, if this is what my remainder term is going to look like, when is that remainder going to be less than 0.001? So it's just a matter of taking this expression right here and forcing it to be less than 0.001. And then we have to use a table on our calculator to determine that. So if we pull up our calculator, in my y equals, we're just going to type in that remainder term. So 3 times 0.75 raised to the x plus 1 divided by x plus 1 factorial. Be really careful with your parentheses there. And then we're just going to go to our table command. And these are the different values that we would get for the different n choices. So if n was 1, we'd get 0.84. If n is 2, 0.21. If n is 3, 0.039. And what we're looking for is the first time when this remainder term gets smaller than 0.0001. So if you look at the fifth term here, 7.4 times 10 to the negative fourth would be 0.00074, so that's too big. But if you look at number 6 here, this would be 0.000079, so it's got 4 zeros. So this is the one that's going to first be less than 0.01. So that's what I'm going to write down. When n is 6, this error gets smaller than 0.0001. So when n is 6, this remainder is 0.00079, which is less than 0.0001. So what we want is to use n equals to 6, which means we want a degree 6 polynomial. The number that you end up with here is the remainder n, the n that you use in this remainder formula, but it's actually the 7th derivative, since we're using n plus 1 up here, that you're looking at. So just use whatever that first n is that works, and that's the degree of the polynomial that you're going to use to make sure, or to ensure, that your error is smaller than 0.0001. All right, let's try one last example. Determine the value of x such that the function sine of x can be replaced by its third degree Maclaurin polynomial if the error is to be less than 0.0001. Okay, so this time what information am I telling you? I'm telling you the degree, the third degree Maclaurin polynomial. I'm telling you what I want the error to be, but what I'm not telling you is the value of x that we're plugging in to get an approximation for. So slightly different information. So where do we start? Well, we want a third degree Maclaurin polynomial. So let's go about finding that first. So our function f of x is sine of x. And if we want a third degree, then we're going to need a first derivative, a second derivative, and a third derivative. So the first derivative is cosine, second derivative is minus sine, and third derivative would be minus cosine x. This is a Maclaurin polynomial, so that means we're using zeros for these derivatives. So f of 0 will be 0, f prime of 0 will be 1, f double prime of 0 will be 0, and f triple prime of 0 will be negative 1. So what will this polynomial look like? Well, sine of x will approximately be the very first constant term, which is 0, plus the first derivative, 1, divided by 1 factorial, which is still going to be 1, times x. So that'll just be a 1x. The second derivative is 0, so then our third term here is going to be a minus from that 1, minus 1, and then it's going to be an x cubed over our 3 factorial. So this is our third degree Maclaurin polynomial. If we're using a third degree polynomial, then what's the remainder incurred by using that? Well, it's going to be the fourth derivative at some value z divided by 4 factorial times x to the fourth. So we're going to need to bound this fourth derivative somehow. Well, what do we know about the fourth derivative? The fourth derivative is just going to be sine of x. So this is going to be the sine of z times x to the fourth over 4 factorial. So can we bound the sine of z somehow? Do we know something about sine of z? Well, we know in absolute value it's always less than 1 because it oscillates between negative 1 and 1. So in absolute value, this remainder is going to be less than or equal to, plugging in a 1 right here as my bound. So this is going to be less than or equal to x to the fourth over 4 factorial. Now that's what our remainder is. Normally at this point then we would plug in the x value that we're trying to approximate at, like our 0.5 or our 0.75, but they're not telling me the value of x. They're telling me what they want this error to be. So they want this remainder to be the error less than or equal to 0.001. Let's just make it less than to fit with how this is described in the instructions. Strictly less than 0.0001. So now if we try to solve this, this will tell us the value of x that will ensure that we're within that error. So what can I do here? Well, I can multiply by my 4 factorial, which is just 24. So this is just going to be 0.0024. And then if I take a fourth root of both sides, then that gives me that x has to be less than the fourth root of 0.0024 is about 0.2213. Now remember that we're using Maclaurin series here, so we're centering it at 0. So what this tells us is that as long as I use a value of x that's less than 0.2213 and I plug that x value into this Maclaurin series, my accuracy will be within 0.0001 of the true value of sine of that x value. So as long as my x's that I'm plugging in are less than 0.2213, this will be a fairly accurate approximation. So that's what we just found out. Okay? All right, that concludes our video lecture on Taylor polynomials and approximations. Good luck!